Okay. So, hi everyone. Uh, I'm happy for you to be here. Sorry, I'm a little bit yeah. Okay, so today we have Professor Ana Cristina Barreto. She's a postdoctoral researcher at the Federal University of Ceará in Fortaleza in Brazil. She's gonna talk to us about Hölder regularity of the top Lyapunov exponent for random matrix products with a one-dimensional equator. And so thank you for being here, Ana Cristina. Uh, and so
Hello,
you can,
everyone.
okay.
Okay, thank you.
Yeah.
Thank you. Can you hear me? Yeah?
Yeah, we can hear you.
Okay, thank you. Hello, everyone. Good morning. Um, First, I would like to thank Professor Adriana Sanchez for the invitation. It's a great honor for me to be here. I'm very happy. Thank you very much. So, this work was developed during my PhD under the supervision of Professor Marcelo Viana from INPA and Professor Adriana Sanchez and Yaya Tao from Universidade de Costa Rica. So um, we were interested in studying the regularity of the top Lyapunov exponent for a certain system that we call random matrix products. And when the equator is one-dimensional, we could prove that the top Lyapunov exponent is Hölder continuous. Okay, I hope that the title and our contribution becomes clear during the presentation. First, I would like to talk a little bit about the system. Okay, so sorry. Okay, okay, about the system. So consider the space of all real invertible matrices of size d times d. Okay, from now on, we will denote this space by G. And if we keep this space with its Borel sigma algebra and a probability measure, we will have a measurable space, right? Now, consider the sequence space with the product sigma algebra and the product measure, right? And now in this sequence space, we will define random variables, ki, where uh, each one of these random variables are projections in the specific coordinate, okay? So uh, key key 2 will be the projection on the coordinate numbered with a 2, right? And so on. So what we want to understand is the product of these random variables. What are the people were interested in understanding the probabilistic properties of this product. Okay, and for us, the first question we want to answer is if the limit, this limit here, so we have here the norm of the product, right? We take the log and we divide by n. Does this limit exist for almost every sequence? And the answer is yes. Under an integrability assumption, we have that this limit exists almost everywhere. And more than that, Furstenberg-Kasten theorem tells us that the co-norm also converges almost everywhere, right? These two numbers here, lambda 1 and lambda d, are known as the extremely Lyapunov exponents of the system, right? And the top Lyapunov exponent, lambda 1, measures the maximal asymptotic exponential growth rate of the random matrix product. So we can understand this limit uh, like this. Imagine that for a n sufficiently small, we can think about the growth of this norm as being almost the exponential of n lambda 1. Okay? So when lambda 1 is bigger than 0, is positive, we have exponential growth. And when lambda 1 is negative, we have exponential decay, right? So here we have taken a first look at the system from a probabilistic point of view, right? But now I want to show another perspective of the same system, the dynamical system perspective, okay? And the main tool we use to understand matrix products dynamically is the linear cocycle. So let's define it. So again, we have the set of real invertible matrices, right? Of size d times d. We endow this space with this distance, delta, and we consider the space of probability measures with compact support on G, okay? From now on, all probability measures on G will have compact support, all right? So consider a probability measure there in this space with compact support. Again, we consider the sequence space, and now we define two maps. The first one is the shift map, very important in dynamical systems in general. The shift map takes a sequence and shifts it to the left, right? And the second map is a projection map, but now different from the random variables that we saw before. We only define one projection, the projection on the first entrance, okay? So we take a sequence and this map gives us G0, which is the matrix in the first entrance of the sequence, okay? All right, with these two maps, we can define the linear cocycle defined by A over sigma, which is given by this map F, okay? So notice that in the first entrance here, we have the shift map applied to a sequence, this sequence G. And in the second entrance, we have the projection, which gives us a matrix applied to a vector in Rd. Okay, so this is the linear cocycle. Now we have a map that when we iterate this map F n times, what we get is here in the first entrance, we have the shift map applied to the sequence n times, all right? But in the second entrance, something interesting happens, right? Because when we iterate this map, what appears here is the product of the first n matrices of the sequence G applied to a vector V. So in some sense, we can understand the product of matrices, understanding the linear cocycle, all right? So the product of matrices appears here in this second entrance. Nice. So under under the same integrability assumption that we saw before in systematic casting theorem, here in Ozella-Dad's theorem, we have that not only may exist two Lyapunov exponents, the extremal ones, but this theorem guarantees that there exists a whole spectrum of exponents and also a flag. We can call it also a filtration of Rd. It means that we have some subspaces, and this theorem tells us that the limit of imagine that we have here the product of matrices, right? But applied to a vector, because we are thinking about this behavior here in the linear cocycle, right? So applied to a vector here. This growth, this limit, depends on where the vector v is in relation with respect to this flag here, right? So if v belongs to this set, we have that this growth is lambda I, right? So the Lyapunov spectrum tells us where these limits are going depending on this vector v. the position of the vector v in this flag, right? And this is interesting for us because knowing the existence of these Euclidean subspaces allows us to define what is the multiplicity of a Lyapunov exponent. We have a whole spectrum, and an exponent can appear more than once in this spectrum. So we call the number of times that an exponent appears in this spectrum its multiplicity. We can also define it as the difference of the dimension of the corresponding Euclidean subspace and the next one. Okay? So we say that our Lyapunov exponent is simple when its multiplicity is equal to 1. And this is important for us because we will see that one of our assumptions is that the top Lyapunov exponent, lambda 1, is simple. So its multiplicity will be equal to 1. Okay? And we can also see here that since our system is ergodic, it follows that the Lyapunov exponents are constant almost everywhere. So the exponents does not depend on the sequence we choose. It only depends on the probability distribution U. So we can see lambda 1 as a function of this distribution. And a natural question is, if this is a function, a map, how lambda 1 depends on the probability measure, right? So we are interested in answering this question. And there are some previous work that consider this question also. For example, Boca-Viana, they proved that the Lyapunov exponents are continuous with respect to some topology that I will define later. In the 2x2 case, this means that they are only considering smaller matrices, right? 2x2 matrices. Then Avila and Viana proved continuity using the same topology, but now for matrices of arbitrary dimension. Recall that I'm talking about regularity with respect to the probability distribution, right? So they are saying that the Lyapunov exponents are continuous functions with respect to this probability distribution. But then we can ask, what is the moduli of continuity, right? Are these functions Hölder continuous, for example? And Lepage proved that the top Lyapunov exponent is local Hölder continuous, but he assumed a stronger irreducibility and a contraction property. These two assumptions together implies simplicity of lambda 1. Recall that I say that lambda 1 is simple when its multiplicity is equal to 1, right? So the question was, is simplicity enough to prove Hölder regularity for the top Lyapunov exponent? And Tau and Viana proved that the answer is yes. They couldn't achieve local Hölder continuity, but they achieved pointwise Hölder continuity when the top Lyapunov exponent is simple in the 2x2 case. So the main inspirations for our work are these two papers that I showed before. What we asked is the following. Okay, Tau and Viana proved that Hölder continuity is possible in the 2x2 case, only considering that the top Lyapunov exponent is simple. Can we extend this result to higher dimensional matrices, right? For arbitrary dimensional matrices. We had a hope that it would be true because Avila and Viana has a whole theory for higher dimensional matrices. So maybe we can use some of its tools to improve this result here for higher dimensional matrices. So the question is the following. Now we are in the D by D case, okay, bigger matrices. And assuming that the support of the measure is compact, that lambda 1 is simple, and we needed to put an additional assumption that the equator is one-dimensional, we want to determine if the map lambda 1 is pointwise Hölder. The Hölder continuity means that we want to prove that there exists a neighborhood of mu and constants such that this inequality here is true. Sorry. This inequality here is true for every mu prime in the neighborhood of mu. Okay? So to understand better this additional assumption here, this third one, we need to define what is the equator, right? So let's do that. We say that a subspace in RD is mu invariant if it stays fixed by all the matrices in the support of the measure. Okay? So a mu invariant subspace is a special subspace of our system. But there is a more special case, which is the equator, that is a maximum mu invariant subspace that has this property here. When we compute the growth rate of the norm restricted to the equator, this growth rate is strictly smaller than the top Lyapunov exponent. Okay, so in some sense, the equator encodes all the vectors that grows in a small rate, at least smaller than the top Lyapunov exponent. So, for example, sorry, thank you. For example, consider this system. We are here in the case where D is free, and we have this probability measure mu. There is a sum of Dirac masses, right? And these matrices A1 and A2 are given like this. These are the definitions. The most important thing here is that this system has two invariant subspaces. The first one, there are some vectors in here that grows with lambda 1. So this first invariant subspace cannot be the equator, right? Because I want it to grow strictly smaller than lambda 1. So in this case, the new equator is the second subspace here that corresponds to exponent lambda 2. And notice that in this case, the dimension of the equator is 1 and lambda 1 is simple. The multiplicity of lambda 1 is 1. So this is exactly the kind of system that we are interested in. Okay. So now we can state the results. This is our contribution. We prove that when the top Lyapunov exponent is simple and the equator is one-dimensional, small perturbations of the probability distribution produce a Hölder variation of the top exponent. We could prove that the top exponent is pointwise Hölder continuous with respect to the probability measure. Notice that when we talk about continuity, we only need topological spaces, right? But here we want to prove Hölder continuity. So we need a numeric estimate in the sense that this difference between exponents is smaller or equal than a constant times the distance between the measures, right? So we need to keep the space of probability measures with compact support with a distance. Right? And I didn't define yet, but I will soon. And so we need a metric space, right? We saw before that Boker-Viana and Avila-Viana proved continuity in this context, right? So there they define a topology T, which is this one. Is the smallest topology such that these two properties hold, right? The first property gives us the weak star topology, And the second one is a pullback of a Hausdorff topology in the space of compact subsets of G. Well, they could prove continuity with this topology, and in the work of Talviana, they defined a distance in the space of probability measures with compact support that metrizes this topology. Okay, so what is this distance? It's actually a sum of two distances. The first one is the Wassenstein distance, which metrizes the Weak-Star topology, and the second one is the Pompeu-Hausdorff distance. This second distance here appears because we want to guarantee that when two measures are close, we want to guarantee that their supports are also close. Okay? So nice. Now we can fully understand this statement, right? We know what the equator is, we know what's the distance. So let's talk a little bit about the tools we use to prove this theorem, okay? Well, I defined a linear cocycle in RD before, right? But actually, we don't work in RD. We work in the projectivization of this space, which is this projective space here. We can see the projective space as the first Grassmannian, if you like. It means that every element of the projective space is actually a line passing through the orange of RD, right? An element of this space is a direction in RD. We keep this space with this distance. And there is a natural action of the group G on this projective space. And since this action is well defined, we can define the projective cocycle. So instead, we replace RD by the space P here, the projective space, and we define a similar cocycle. Here we have the shift map, and in the second entrance, we have the projection, but now this matrix is acting on an element of the projective space, okay? There are some advantage in working with the projective space. One of the advantages is the fact that this space is compact, right? So it gives us a lot more freedom to work with. Okay? So in this setting, we can define what is a Markov operator. So we take a bounded function in the projective space, and the Markov operator acts on this function like this. It's like a mean of the pullbacks, right, by the matrices G. And what we are really interested in is the dual Markov operator, because this dual operator, it acts on measures like this. So if we apply it to a measure eta, it gives us the mean of the push-forwards, okay? And we say that a probability measure on the projective space eta is mu stationary if it is a fixed point of the Markov operator. And these stationary measures are very important for us because they help us to write the top Lyapunov exponent in a very nice way. Notice that by this result, the first exponent is the supremum of these integrals here over all the stationary measures, right? And we know more. We know that this supremum is attained, okay? So there exists a stationary measure such that lambda 1 can be written in this integral formula here. And when this happens, we say that eta is maximal. So it's a maximal stationary measure, okay? That's awesome because we want to obtain estimates with lambda 1, right? So it is very good that we have an integral formula for lambda 1. So having these tools in hand, we can discuss a little bit about the outline of the proof of the theorem. Okay? So first of all, we need to consider a probability measure with compact support and lambda 1 simple. These are our assumptions. Okay. Then we express lambda 1 using the integral formula that we just see. Okay? We just saw, sorry. So this difference here between lambda 1 of mu and lambda 1 of mu prime can be written as this difference here of the integral formulas. After some computations, we arrive in this Lipschitz estimate here. This is exactly the kind of thing we are looking for, because we have here that the difference is smaller or equal than a constant times the distance between mu and mu prime, which is also. But there is a second term here that depends on the distance between eta and eta. Recall that eta and eta prime are probability measures on the projective space, right? Eta is maximal stationary with respect to mu, and eta prime maximal stationary with respect to mu prime. And here we have the distance between these two. So we need to put a distance in the space of probability measures on the projective space, and the distance we choose is a Wasserstein distance. Okay? So now we reduce the problem to estimate the distance between eta and eta prime, and we arrive at this estimate here. Notice that in the first term, we also have the distance between mu and mu prime, which is good. But in the second one, we have the distance between iterates of the dual Markov operator, right? And also notice that here in the first term, we have a constant, which is greater than 2, and we have an exponential term here, right? So this term is getting bigger and bigger as n goes to infinity. So what we want is to prove that this distance here has the opposite behavior, right? We want to prove that this is getting smaller and smaller as n goes to infinity. In other words, we want to prove that the Markov operator is a contraction. Right? So actually, the main difficult part of this proof is to prove exactly this, that the Markov operator, the dual Markov operator, is a contraction. So what we achieved actually is that this distance is smaller or equal than a term like this, where tau 1 is a constant between 0 and 1. So this is getting smaller and smaller, right? Notice that if we can prove that this distance is actually bounded by this term, after some computations, we arrived at the Hölder regularity that we want. The difference between lambda 1 and lambda 1 of mu prime is smaller or equal than this term here. And we get the Hölder continuity, right? So let's try to prove that this distance is actually bounded by this term, okay? So we are, to begin to start this computation, let's see the definition of this distance, okay? So the Wasserstein distance between these two measures is the infimum of these integrals here, which is the distance between the points, and they are integrating with respect to a measure, which is a coupling of the two measures, right? So since this is an infimum, we can choose a specific coupling that is more convenient for us. And after we do this, we arrive at these inequalities here, right? And then let's take a closer look to this integral that appears in the last line. Okay? Notice that we have a triple integral, and we are integrating the distance between GU and GU prime with respect to a measure that is the nth convolution of mu, right? And eta and eta prime, there are stationary measures. Okay. This nth convolution, by definition, you can see here in the blue box, when we have the convolution here, where we have G, actually what appears is the product of any matrices. And these matrices are in the support of mu. So when n gets bigger and bigger, we are actually applying more and more matrices here, more and more products of matrices. And we want to understand what happens with the distance between these images, right? Of u and u prime by this product of matrices, which is our system, right? Okay. The good news is that when when u and u prime are far from the equator, we can control this distance exactly the way we want. Everything works perfectly. For this, we can bound this integral by an exponential term exactly as we wanted. And for this, we use finite time large deviation estimates. Okay, everything works well. But when one of these points, u or u prime, is close to the equator, we don't know how to control this distance. Everything we did here does not work when we are close to the equator. So we need to use a different approach for points close to the equator. Since we can't control the distance, our strategy was to control the masses, right? Because we have probability measures here. So if we can control the mass of the stationary measures near the equator, we can bound this integral in a good way. So for this, to have control over the masses, we introduce a new definition that we call a measure being balanced. What this means? So that's the definition. We say that a measure is balanced if, you can see here in the picture, mu is balanced when there is a neighborhood of mu, such that for everyone in this neighborhood, there exists a maximal stationary measure that satisfies this bound here, right? So look at this bound. We are measuring the neighborhood of the equator with radius r, right? And it tells us that for this neighborhood, there is a very nice behavior, right? Because L and B are uniform constants, uniform for R and uniform also for the neighborhood, okay? So everyone in this neighborhood behaves in a same way, has this nice behavior near the equator. Okay? So for this kind of measures, we were able to prove exactly what we needed, that the distance between the iterates of the Markov operators decays over time exponentially, right? And well, for this, we need the balanced property because our strategy was to, far from the equator, we use the large deviations that I talked about, and everything works well in this blue area. And in the purple area, where one of the points is near the equator, we use the balanced property, and we can bound that triple integral in a nice way. So if our measure is balanced, everything works well, and we can prove the theorem. Okay. So the next question is the measure balanced or not? And the answer is yes, but we can only prove this when the equator is one dimension. Okay, so this is the first time in this seminar that the dimension of the equator is important, right? Everything else that I talked about until now works well for equators of any dimension. But the balance property, we could only prove it for one-dimensional equators, right? And the tool we use to prove is theorem B. It's this theorem here. So if we have a probability measure with complex parts and a one-dimensional equator, we can prove that for all generic measures near this measure nu, the stationary measures behave like this near the equator. Notice that this estimate tells us some kind of scaled behavior, right? So at some scale, we can control the rate, the mass near the equator by this term 2/3 here. And with theorem B, after we prove theorem B, we can iterate this estimate and choose constants B and L and prove that our measure nu is actually balanced, right? Has the balanced property. So with this in place, since theorem B implies that mu is balanced, then theorem A follows, right? So uh, let me resume everything that I talked here. So under our assumptions, the top Lyapunov exponent is pointwise Hölder continuous at mu, and the main obstruction comes from the concentration of mass near the equator, and a one-dimensional equator allows us to get a uniform control of this concentration. So natural questions arise, right? The first one is, does the key estimate in theorem B remain valid for higher dimensional equators? If the answer is yes, we have also the Hölder continuity for higher dimensional equators, right? Because everything else in the proof works for higher dimensional equators. So what remains to be done is to prove that theorem B also is true in this set. Okay? And the second natural question is, can we apply these ideas to other contexts? Notice that we have a strategy, right, to obtain Hölder continuity. And maybe if we have another kind of systems that has an integral formula for lambda 1, and that we can define a set that works as the equator in this new setting, maybe we can adapt our strategy and obtain Hölder continuity in other contexts also. Okay. So that's all I wanted to say today. These are the references. Thank you very much.
Thank you, Ana Cristina. So, are there any questions? Yeah.
Hello.
Hello.
Thank you, Anna, for the presentation. I know how technical this topic can be, and you made it very clear and very easy to follow. I don't have any specific question, maybe some comment about the degenerated case. I think in dimension 2, we prove in Tal Viana that we have also weak moduli of continuity for that. And I recently heard that it was extended in higher dimension.
Okay. Are there any more questions or comments? No? If not, Anna, thank you again for giving us this talk, and again, as Yaya is saying, it was really nice. And so we thank again Anna, and since well, it's kind of hard to clap here, but thank you again for this talk. And just to let people know, next talk will be in 2 weeks. It will be the closing talk for this seminar. It's gonna be given by a professor from Mexico. It's called Gabriela Araujo, and we'll send you the information soon. Again, Ana Cristina, thank you, and
Thank you,
thanks
everyone.
everyone for coming.
Thank you,
Obrigada.
Ana. Obrigado.
Obrigada, gente.
Okay.